Welcome to Study Loop.
Problem number 30 gives us a quasi-real-world example where we have a laser, which I'll attempt to draw a very basic form of a laser, and it has a cylindrical beam of light that comes out of it, in this case, a beautiful blue, and the radius of that cylinder is 2.2 times 10 to the 3 minus 3 meters. And the question wants us to find first the energy that is delivered in each pulse, and each pulse is 1 nanosecond. And then for part B, we want to find the RMS value of the electric field. So for part A, it's not too tricky. We just have to use the fact that power is the, so for each pulse, the energy in each pulse is the laser's power output multiplied by the duration of that pulse. So we're just rearranging this equation here to get that our delta work is P times dt. And we have both of those. So it's 150 joules of energy are deposited with each pulse. So that's not too bad. Part B, on the other hand, is slightly more involved, but it's not impossible, as we'll see. So we want to find the RMS electric field, and we can find that from the intensity, which is power per unit area. So I think this is equation 22-8, and the intensity, which we'll use the average since we want the RMS values, is equal to the power divided by the area. And the area is going to be the cross-sectional area of this cylindrical beam. So I is equal to P over A. You can write this as 1/2 naught C E naught squared. But using the RMS values, it's 1/2 epsilon naught C. So E naught is square root 2 times the RMS value for E. And then you square that whole thing, getting a relationship like this. And we want to solve for ERMS, so you just shuffle things around slightly. And you get that the expression is simply P over A C epsilon naught. And we have the power, and we can figure out the area because it's just pi r square. And that is all equal to 1.9 times 10 to the 9 volts per meter.